Welcome to The Explainer. Today, we're diving into the bizarre, absolutely fascinating quantum world. To kick things off, I want you to picture something for me. Imagine a futuristic, neon-lit coin just spinning in midair right in front of you. It's set against this dark background, and as it spins, it's moving so incredibly fast that it visibly shifts and blurs between a glowing blue heads and a vibrant pink tails, all at the exact same time. Now, why are we starting with a neon coin? Well, researchers over at Vrije Universiteit Amsterdam were actually looking into the absolute best way to explain quantum technology. And they found that visual metaphors, exactly like our spinning coin here, are a total game changer. They really help people grasp these wild quantum phenomena. Because let's be honest, giving our brains a familiar image is pretty much the perfect bridge to understanding the unimaginable. Okay, let's dive into this. Here's the journey we're going on today. First, we'll look at the spinning coin analogy. Then we'll properly define quantum superposition. After that, we're tackling Schrödinger's cat paradox, the measurement problem, a few mind-bending interpretations of reality, and finally, we'll wrap up with how quantum tech meets art. All right, section 1, the spinning coin analogy, a blur of states. So bring that neon coin back to mind. It's suspended right in front of you, spinning so fast it's just this glowing blur. Now let's contrast our everyday world with the quantum realm. A normal classical coin toss, that's completely deterministic. If you had a super fast camera and could measure the initial spin, the air resistance, the friction on the table, you could predict exactly how it would land. It's literally just a matter of having enough data. But a quantum coin toss, that is fundamentally probabilistic. While it spins, it doesn't just lack a decided face. It actually exists in a simultaneous combination of both states, carrying something called quantum phase. It's wild. Nature itself genuinely hasn't decided yet. Let's walk through the life of this quantum coin. Step 1 is the spin. This is the superposition, the literal blur of possibilities. Step 2 is the slap. That's when you forcefully bring your hand down to stop the coin. In the physics world, this represents the act of measurement or observation. And finally, step 3 is the result. It is only the exact moment you make that measurement, the moment you slap your hand down, that the blur instantly collapses into a single solid state, heads or tails. Moving right along to section 2, defining quantum superposition.
Let's ground our spinning coin metaphor in the actual terminology that physicists use. Now, what's really interesting about this is that it isn't just some handy metaphor for human ignorance. We aren't just saying, we don't know. Quantum superposition is the absolute principle that a particle genuinely exists in multiple states at the same time. The math of the linear Schrödinger equation literally demands it. This equation shows that if state A is a valid solution and state B is a valid solution, well then A plus B is also a valid solution. The particle is actually in all states together, right up until it's measured.
So what exactly happens when we do measure it? We get what's called wave function collapse. This is the precise moment a quantum system interacts with the external world. And here's the kicker. Any interaction that extracts information counts as an observation. Whether that's a human looking at it, a detector pinging, or honestly, even just a stray air molecule bumping into the particle, that destroys the superposition. It forces a single definite outcome. All right, on to section 3, Schrödinger's cat paradox, a famous paradox. Now we have to talk about the most famous and honestly most often misunderstood thought experiment in all of physics history. It scales this microscopic weirdness all the way up to something we can visualize. Back in 1935, Erwin Schrödinger wrote, "One can contrive even completely burlesque cases. A cat is put in a steel chamber along with the following infernal device." Now, a lot of people don't realize this, but Schrödinger actually created this paradox to mock Niels Bohr and Werner Heisenberg's views. He was trying to show how totally absurd it is to take this quantum indeterminacy and scale it up to a macroscopic living creature. Let's walk through the timeline of this experiment. At 0 minutes, the box is sealed. Inside, you've got a radioactive atom, a Geiger counter, a vial of poison, and, of course, the cat. The atom is intact, the cat is alive. Jump to 30 minutes. Quantum mechanics says that the unobserved radioactive atom enters a superposition. It is both decayed and not decayed. And because the cat's fate is completely tied to that atom's state, the entire system becomes entangled. The cat is mathematically both alive and dead simultaneously. It's not until 60 minutes, when the box is finally opened and observed, that the wave function collapses into a single reality. Which brings us to section 4, the measurement problem, the core contradiction. This leads us right to the core paradox. Why on earth does looking at something fundamentally change its physical nature? This contradiction is known as the measurement problem.
See, the Schrödinger equation predicts this continuous deterministic evolution of probabilities, but the actual active measurement, that causes a random instantaneous collapse. And here is the reductionist issue. If the universe is entirely made of quantum particles, well, human observers and detectors are made of those exact same particles too. So why doesn't the superposition just spread to us when we open the box, instead of collapsing? As the legendary physicist John Wheeler famously put it, no phenomenon is a phenomenon until it is an observed phenomenon.
So the crucial takeaway here is that 50% is the absolute limit of predictability for an equal quantum coin toss from a superposition state. Unlike classical mechanics, where better measurements give you better predictions, in the quantum world, random chance is baked right into the very fabric of reality. You simply cannot know the outcome until you look. Section 5. Interpretations of reality. What is reality? Because physicists still do not agree on what actually happens during that metaphorical slap, the measurement, we are left with several brilliant, completely competing interpretations of reality itself. Let's impartially break down this matrix, and keep in mind we're not taking sides here, just looking at the options. First, the Copenhagen interpretation says measurement simply triggers the collapse. The cat is dead or alive only upon opening the box. Then there's the many worlds interpretation. This one argues there is no collapse. Instead, reality itself splits, meaning the cat is both alive and dead, but in entirely separate, branching universes. The relational interpretation suggests that the state depends on the observer's information, so the cat and the human actually have different accounts of reality until they share them. And finally, Bohmian mechanics suggests hidden variables are at play, guiding particles to a definite yet completely hidden outcome right from the start. Like I said, these are just the fascinating ways science attempts to explain the ultimate nature of our universe. Let's move to Section 6 and see how this builds into the real world. Quantum tech and art, modern applications. We are actively using this bizarre science in the real world right now. Just look at these incredible applications. In quantum computing, we are preparing weighted superpositions to solve insanely complex algorithms. In physical labs, scientists have actually created macroscopic tuning forks. We're talking trillions of atoms that are somehow vibrating and not vibrating at the exact same time. Over in the visual effects industry, artists are literally using the Schrödinger equation to generate these gorgeous vortex-like smoke effects, called Schrödinger smoke. And researchers are even exploring quantum supersampling, which means placing pixels into a superposition to evaluate renders simultaneously, drastically cutting down on processing times. And this slide brilliantly illustrates how quantum computing actually works in practice. It doesn't just use 50-50 coin tosses, it engineers weighted superpositions using that quantum phase we talked about earlier. Imagine our neon coin, but now it's spinning at a really steep angle. The quantum computer adjusts the phases so that constructive interference boosts the right answer, while destructive interference cancels out the wrong ones. So when the wave function finally collapses, the correct answer is overwhelmingly likely. We're talking like a 90% chance for the desired outcome versus 10% for the incorrect one. But it's not just technology. This concept is actively shaping modern visual design too. Think about AI art and modern graphics. They rely heavily on this neon aesthetic: electric blues, vibrant purples, striking whites. These neon colors are specifically used to visually represent the mysterious, highly energetic flow of wave-particle duality and entanglement. It's an amazing way to bridge this highly futuristic, abstract quantum realm with a nostalgic, tangible human reality. So, after all of this, we're left with a truly profound concept to reflect on regarding our vast cosmos. Does the universe only exist in a solid, definite state because we are here to observe it? The quantum coin is still spinning. If observation is what collapses the wave function, what exactly is your role as an observer in this universe? Until you decide to look, to measure, to interact with the world around you, all possibilities remain completely open. Thank you so much for joining me on this explainer today. Keep wondering, keep observing, and I'll see you next time.